Good? Sort of? Okay. Doing okay? Okay is not too bad. Good. So, shortly before this class began, I posted an announcement on Avenue on the subject of the upcoming midterm. So we have a test on Saturday. This test, I'll just briefly run through the procedure for it. It's going to be an online test. It's going to be an open book test. So you're permitted to use aids such as the Python documentation, Wikipedia, that type of thing. You are, of course, strictly prohibited from speaking to, interacting with, or sharing any kind of information whatsoever about the test with anybody present or not present in this room. So anybody on the planet, with the exclusion of the TAs and myself. So the test will be distributed through the normal means of distribution on both Jupyter Hub and Avenue. You are permitted to select whichever of the two of those most suits your purposes. The test will begin at 9 o'clock a.m. Eastern Standard Time. That's when the test will become available. You have 24 hours to complete the test and get it in before 9 a.m. on Sunday. People with SAS accommodations, of course, have their requisite extensions. So you have an unlimited amount of time to perform the test within that 24-hour window. We have not designed the test to take 24 hours, although always we have a few people who decide that that's, the thing that they want to do with their Saturday night is pull an all-nighter on the test. That happens every time, despite the fact that in the opinion of this professor, such behavior is not only completely unnecessary, but detrimental to one's health and all of that kind of jazz. So, anyway, are there any questions about the test before we move on with the lesson today? Normally there are at least a couple. No? Everybody's going to get 100% then? Question?
Sorry, I don't know if I missed this top. Is it going to be similar to the assignments in terms of the way it's class?
It's going to be shockingly similar to the assignments. You may even think that instead of giving you a test, I've given you an assignment to write as a test. That's entirely a thing that might go through your brain as you're writing this test. But I assure you, it is a test, because I said so. Any other questions? Yes?
Will it be fun?
Will it be fun? Well, that's up to you, really. I think some of the questions are kind of cool. There's definitely one that it's like, I know the students are probably not going to like this question, but there's, and you know which one I'm talking about. But there are a few there that are kind of cool, I think, that are sort of relevant to pop culture and stuff. Yeah. Any other questions? I guess whether or not you find the test fun depends on whether you find the assignments fun. Yeah? All right. Good. So, might as well keep moving right along today. We have material which is somewhat heavier in nature to slog our way through today, so we will do our best to keep a stiff upper lip and keep soldiering on through the interminable wastes that are floating point representation. So, we of course recall that when we're programming, we have two primary numerical representations for, numbers. We have integers, of course, which we've talked about at length. And then we also have floating point numbers. In standard mathematical jargon, we would call these the real numbers. Although floating point numbers are not exactly the same thing as the real numbers, they do not, like, floating point representation does not represent the complete set of real numbers. It could not possibly. The set of real numbers is infinite, and computers are not. In the same way that not every integer can be represented using the integer representation, not every real number can be represented using floating point notation. But it does a pretty good job. So, if we express fractional numbers inside of the binary system, and you're going to watch me trip this up, because this is a decimal point, but this is not a decimal number. This is a binary number. So does that make this the binary point? Well, philosophical questions for your Wednesday afternoon. So, in the same way that we have increasing powers of the base on the, what is this, left-hand side of the decimal or binary point, we have decreasing powers on the other side, starting with -1. This means that the numbers which are represented, which can be represented inside of binary fractional representation, must be a sum of fractions with a power of 2 as the denominator. Right? So we can only represent things like 1/2 plus 1/8 plus 1/64 plus 1/1024. Right? These are the only types of numbers that can be represented with finite precision inside of the binary system. And we're going to get into what finite precision means. So let's examine point 1, right? Point 1, of course, has, in decimal at least, point 1 has a very easy fractional representation. What's the fractional representation of point 1? Anybody? Yes? 1/10. Yes, very good. 1/10. Is 10 a power of 2? No. We're going to see how this causes problems. So let's try to use 3 binary fractional digits to get as close to 0.1 as we can. Well, we end up with 0.001. That is 1/8, which is equated to 0.125 in the decimal system. This is definitely not very close to 0.1, but we're trying. This is too high, right? What happens if we add 2 additional bits of precision? We can come up with a representation 0.00011. This is 1/16 plus 1/32, which is 3/32, which is 0.09375 in the decimal system. So you see, by adding 2 additional bits, we get a closer approximation of 0.1. But we're certainly not there yet, are we? So what happens if we add an additional 4 bits of precision? So now we've got 9 bits of precision in total. We can hit 51 out of 512, which is 0.099609375. Again, we are coming very close to 0.1 without actually hitting it. The answer here is that in order to represent 0.1 exactly inside of a binary representation, you would need an infinite series of repetition of these last 4 bits. Right? In the same way that 1/3 cannot be represented with finite precision in the decimal system, 1/10 cannot be represented with finite precision in the binary system. Incidentally, 1/3 can also not be represented with finite precision inside of the binary system, because this is, again, not reducible to powers of 2. Does that make sense? Good. So okay, so that's a lot of math, but how is this actually computers, right? Obviously, computers are not infinite in their scope. The memory that they have is finite. It's actually a lot worse than that. The memory which they can functionally operate on at any given time is very, very small in comparison to the actual storage size of the computer itself. So, essentially, under current architectural limitations, we have at most 64 bits for this, right? That would only get us so far. That gives you a very good approximation. It turns out that it turns out that if you use about 16 of these bits, you get a close enough or not 16. Well, anyway, we'll get the numbers specifically. We subdivide those 64 bits. We use some of them to represent this fractional component. We use the rest to indicate magnitude in the same manner as scientific notation, and that's what floating point is, essentially, right? But it's very, very important to note, when you enter 0.1 into your computer, you are not actually entering 0.1. You are entering a number which is very, 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 very close to 0.1 without actually being 0.1, which of course is the reason why if you add 0.1 together with itself 10 times, it does not equal 1 perfectly because those errors will accumulate over time. Does that make sense? Any questions so far? Okay, good. So, yes, infinitely many binary digits are needed after the initial digit of 0. The digits 0, 0, 1, 1 keep repeating. And you sometimes see this in the decimal system as well. Sometimes you'll get like a number that it goes like 7, 8, 7, 8, 7, 8, 7, 8 off to infinity. It's a similar idea. It doesn't have to be a single digit that repeats. It can be a sequence of digits that repeat. And if you all remember the difference between rational and irrational numbers, what's the difference between a rational and an irrational number? Anybody? Nobody? Sorry?
All I know is a rational number has a complex part.
Rational number has a complex part.
Irrational.
Irrational. Yes. Well, let's not talk about that. Let's go back to like the definitions of them, right? What does rational mean? Yeah. Yes, yeah. It's like the roots of the word rational is ratio, right? A rational number is the ratio between two other numbers. That's what defines a rational number. An irrational number is a number which cannot be represented as a ratio of two other numbers, right? We're going all the way back to Pythagoras for this. So if you take a number, for example, like pi cannot be represented by it cannot be perfectly represented by the ratio of two other numbers, right? You can get pretty close though, right? That's not to say that there aren't rational approximations of irrational numbers, but the number itself is irrational. But anyway, you can tell the difference between a rational and an irrational number by the fact that you have repeating sequences. Even if it goes off to infinity, if there's a repeating sequence as it goes off to infinity, that means that it's a rational number and not an irrational number. Right? Good. Excellent. Well, I kind of already answered this one for you. But which of 3/4 and 1/3 have finite binary representation? Who thinks both of them do? Who thinks only 3/4? Who thinks only 1/3? Who thinks that they don't know the answer to that question? I hope that nobody doesn't know the answer to that question, because, like, man, that would be like a short-term memory problem, you know? Because I literally just said it. Anyway, so now we come to the somewhat thorny issue of how practically we decide, of these 64 bits which are available, how many of them are we dedicating to the fractional component, and how much do we dedicate to how large, what the magnitude of that should be, right? So this has been standardized. It has been standardized since, I believe, the 1970s. So the IEEE, I believe it's International Electronic and Electrical Engineers. I think that's what the acronym stands for. If anybody knows what IEEE stands for, please tell me. I should know the name of an organization of which I was formerly a member, because I stopped paying the dues because, whatever. But anyway, so there are organizational bodies that set standards for these types of things. If different computers used different standards for the representation of their numbers, they would not be able to communicate with each other as freely and effectively as our modern interconnected interweb world now exists, right? If two computers can't agree on how a number is represented, then you need an intermediary between those two computers that translates from one to the other, right? So the easiest thing to do is to standardize. So the IEEE set out a standards document which sets specifically how many bits you use for this and how many bits you use for that inside a floating point representation. It turns out that if you use 52 binary digits, that gives you approximately 16 decimal digits of precision inside of your floating point representation. So let's see, it's 3 is milli, 6 is micro, 9 is nano. What's the one after nano? Atto, femto, something like that? Very, very small numbers, right? If you represented the smallest number in floating point representation, it would be a very small fraction of like the mass of an atom or something like that, Like we're talking very, very, very small numbers. So practically speaking, is anything worth measuring going to have less than going to need less than 16 decimal points? Like, basically, for all practical intents and purposes, this was good enough, right? This is where they decided to draw the line, right? So, when we display numbers, only the first 16 decimal digits are displayed to us, and basically the rest of it is either truncated or rounded up depending on what you're looking at. So, if, for example, where's my, here we go. Was it something I said? So if we have a number like 1/10, we format it so that we're viewing it with 60 digits of floating point precision, you can see that the manner in which the number has actually been represented is it's slightly higher than 0.1. But the slightness of that being higher is lost because 16 decimal digits takes you to 1, 2, 3, well, actually, we can just do it. Why count when the computer can count for you, right? So, with 16 digits of precision, we get a perfect looking 0.1. But if we add one more bit of precision to that, or one more decimal place of precision to that, we see the mirror beginning to crack with respect to the representation. Any questions about this? Okay, good. Are you guys getting this? Like, this is being understood? Okay. Good. Because I know this is like more abstract than the type of stuff we usually do. But so, good. So with finite numbers of digits, arithmetic operations can lead to rounding errors. Sometimes the errors get canceled and sometimes they don't. So, for example, while if you add 0.1 10 times to itself, you don't get 1. That's not true of all numbers. Like if you take 1/6 and you add that together 6 times, you do actually get 1. So it's not that it's not a good system. You know, like it's as good a system as people in the 70s were able to come up with far more bits than they actually had at the time. The problem is that you can't predict whether or not an operation is going to result in errors getting canceled or if it is going to result in errors getting canceled. It's not possible to know it, especially like, you know, it's somewhat facile to just enter a bunch of numbers onto into a command line and press enter. On an assignment, when was the last time you guys like entered a bunch of numbers into a program, right? You're dealing with variables, you're dealing with symbolic content. You are not, most of the time, dealing with raw numeric literals, except insofar as they are interestingly applied variables and arguments. So it's not possible to predict whether or not these errors are going to cancel. So what do you assume? If you have a situation where something bad could happen but doesn't always happen, what do you assume in order to deal with that situation? Yes? You assume that it will always happen. That's right. You plan for the worst and hope for the best, right? So, the question then becomes, how do we tackle these problems, these small errors? Well, in order to get there, we first have to see how and why they become a problem, right? So, everybody should be well familiar and comfortable with equality comparison at this point. If you have these types of errors, which are accumulating in numbers, exact equality comparison will often fail in cases where you think it should succeed, right? If you add 0.1 together 10 times and then say, is that equal to 1, you get false, even though you think it should be true. Whereas, if you add 1/6 together 6 times and you try for equality comparison with 1 on that, you will get true, which you expected and wanted, right? What equality comparison does is it says these two numbers must be precisely and exactly the same, down to the level of the individual bits that represent the number, right? It's a it's actually a bitwise comparison, right? It compares each bit in the two things it's comparing, and if they are precisely and exactly the same, you get true, otherwise you get false. A better way of doing floating point comparison, you take the one number, you subtract the other from it, you take the absolute value of that, and you compare that to some epsilon. Epsilon meaning error. It's the Greek letter that it's a Greek letter often used for error in disciplines like statistics. So, for example, where's my? There we go. So let's. I think it works with 1/3. Let me just see here. There we go. Is that equal to 1 true? Right? But if we have 1/10, four, 5, 6, 7, 8, 9, 10. Well, I should do it to make sure I got it. Yep. So that's false. So what you do is you say 1 minus this, take the absolute value, say is this less than or equal to, say, 0.0000001. Did I do that right? Let me think. Oh, brackets. Jeez. Yeah, there we go. So you can see that if we perform this subtraction, we get a very, very, very small number. So basically, so long as that number squeezes inside some epsilon that you select, you can test that as being true, even though it's not exactly equal, right? The selection of your epsilon doesn't really matter that much, so long as it's small. Like, don't make your epsilon 1,000, because that's going to catch any difference that's less than 1,000, which, you know, in this case would be ridiculous. But, you know, if you just do an epsilon of, like, you know, 6 or 7 decimal places, that'll catch, that'll definitely exclude any floating point error, and at the same time, it's still a useful thing to test. Does that make sense? Good. Excellent. It's more operations, but, you know, so be it. So, I think I'd like to do a little bit on the board now. So now we have a fairly good idea of how we are representing the fractional component of these numbers, right? Remember that the thing that we're trying to reproduce is scientific notation. So, anybody in this room not familiar with scientific notation? Excellent. So if we have like 7.38 times 10 to the negative 3, for example, the important points are this and that, right? We call this the fraction. We call this the mantissa. Right? We take these guys and we represent them in binary code, right? Difference, of course, this is in decimal. So because everything's in binary, what it actually looks like is you have like 1.011101, times 2 to the power of 100,101, etc., right? So you take this. This has, what was it, 54? It was 54. 52. We have 52 bits here. We've got 1 bit to indicate whether or not it's negative or positive. And then the rest are put here, right? To represent the Mantissa. I think it's Mantissa. No, the fraction's called the Mantissa. I'm sorry. Well, this is the exponent. Exponent Mantissa. I'm going to write it. Mantissa. 2 S's? 1 S? 2 S's. Okay. Exponent. There. Now maybe I'll remember. Good. So, we've got 53 here. We've got 1 here. How many remain? Out of 64.
About
11. Very good. Yeah, that was just math, right? Yeah. So you've got 1 bit here, right? You've got 54 or 52 bits here, and then you've got the remaining 11 bits. You fill this up with 1s and 0s. That's what your memory representation of a floating point number looks like. Make sense? Remember, everything is just 1s and 0s. There is nothing inside of memory itself which indicates this is the sign, this is the mantissa, this is the exponent. When you type the memory as float, it automatically interprets it in this manner. That's the purpose of the typing, right? It's not like the memory leaves little tags for itself in here like, this is the start of the mantissa. It's like, no, that would waste so much memory, right? Memory, like, remember that computers as a technology were developed at a time when memory was very, 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 very expensive, right? You had to hand wire each individual bit, right? So they became very conservative with that sort of thing. You don't use any memory that you don't need to use. So yeah. So that's how floating point numbers are represented inside of memory. 11 bits gives us a range of 1,022, or negative 1,022 to 1,023, because it's signed arithmetic, right? Not unsigned arithmetic. This gives us a largest possible represented floating point number of 1.7976931348623157 times 10 to the 308. So 10 to the 308 is very, very exceptionally large. And hopefully well larger than any quantity of anything that we would ever need to represent. This is a number which, like, if you took the universe and assumed that every atom in the universe had a universe inside of it, and so on and so forth, like several thousand universes deep, something like that, you would like, that's the scale at which we're talking with this number and how big it is. Conversely, the smallest number representable is 2.225, etc., times 10 to the negative 308, which is, again, exceptionally small. It's about as small as how much you guys are going to care about this on the test. Whack, whack. All right. So floating point numbers, right? This representation has been standardized. Everything uses this representation of floating point so long as it's IEEE compliant, and trust me, there's no incentive to not be IEEE compliant. This is in everything from your laptop to your Fitbit to your McMaster's standard calculator. This is the way that things are done. There's a trade-off here, right? So when they decided how many bits they were going to put where, the trade-off, if you put more bits in the exponent, you are able to represent a greater range of numbers. If you put more bits into the fraction, you are able to represent with greater precision specific numbers. So, you know, it's not quite the same as, say, you know, they decided that the fraction was 5 times more important than, or the precision was 5 times more important than the range. You actually get more bang for your buck out of exponents than out of fractions, just because each bit that you add to the exponent doubles the number of that doubles the number of numbers that you can represent, right? But yeah, anyway, that's the trade-off. More exponents, larger range, more fraction, more precision. Make sense? Question?
Is one of the exponent bits also like a negative positive bit, like a sign bit?
It's represented in 2's complement. So there's not an explicit sign bit, but like all ones is -1, and if you subtract 1 from that, it's -2, and if you subtract 1 from that, it's -3, until the point at which the first bit reverts and then it flops over to the highest positive representation. So that's how 2's complement works. That's how this is represented. There's not an explicit sign bit inside of the exponent, right? Make sense? Question?
Can you explain why the range is negative 1,022?
Yeah, sure. Yeah. So we've got 11 bits of precision, right? 2 to the power of 11, 2048. Split it in the middle, make half of it negative, half of it positive. That's where that number comes from. Make sense?
Yeah.
Yeah. Because each one of those inside of there has to have a representation, right? So, yeah, that's essentially like how signed versus unsigned arithmetic works. You take a full unsigned range and just kind of bump it down by half of its maximum value, and that gives you the range that you can represent in signed arithmetic. Make sense?
Yeah.
No trouble. Any other questions? Good. Okie dokie. So here's an interesting thing. We have 16 digits of precision in floating point numbers. That means something that is very large in floating point arithmetic can gobble up something that's very small, and it'll just disappear into the number, and you will never see any trace of it again. It's very cool. And that doesn't happen in integer arithmetic. So if I take some 1 with a lot of zeros, and I add 1 to it, in integer arithmetic, the 1 is preserved. Make it a float, and it's gone. You might not be able to see that, but that's 1 times 10 to the power of 23. Let me just put the lights back off for the benefit of everybody's eyes. So, a very brief sidebar, side tangent. If you haven't seen this in computers before, generally speaking, if you see an E, a number, E, another number, E means times 10 to the. Right? That's like the shorthand for scientific notation. Make sense? It can be either a capital or a smaller letter. Sometimes they indicate the sign, sometimes they don't. Make sense? Good. So if floating point is so problematic and so strewn with errors blocking your path, like you're walking through a field of daisies that was recently inhabited by cows who had eaten nothing but burritos for a month, why do we even use floating point, right? It turns out that we do actually have alternatives, right? There are two libraries in Python which you can use to perform these types of arithmetic operations without all of the inherent pitfalls of floating point representation. The decimal library essentially behaves as if it were hand calculation. Python actually does this with integers in the back end. If you try to use an integer that's larger than the largest integer representation, it'll just behind the scenes kind of give you more bits at the expense of runtime and memory. Decimal is like that, but doing the same thing with floating point. And then you also have a library for representing fractions. So, if we have these, why would we use floating point? Any ideas? Class participation time. Yeah.
I was going to say probably more efficient.
Probably more efficient. A lot more cost effective. Cost. Time, energy, and memory. Which is essentially cost in a computing system, right? So, floating point is a standard representation. It's a representation in hardware, right? These are software solutions. The best that a software solution can do is it uses hardware to emulate other functions that the hardware doesn't have natively, right? That costs time in the form of computation cycles. And it often also costs memory. A great deal of engineering effort over the past 5 decades has gone into the development and the acceleration of floating point operations because that is the standard representation. For example, inside of your CPU, or well, they don't really call them coprocessors anymore, but back in the 90s, when the word size of your standard computer might have been 16 bits instead of the current 64, you were still operating at minimally 32 bits for a floating point number, despite the fact that that exceeded the word size of the operating system. So the solution that they had at the time for this problem was they developed what were called coprocessors, which are tiny little chips that plug onto the side of your main CPU, which are designed specifically to accelerate floating point operations. In fact, in the 90s, there was a metric that you would use to classify the speed of a computer called flops, floating point operations per second, right? So you would have a computer that was like capable of, 52 megaflops. And it kind of sounds funny these days because, who talks about flops anymore, Since the word size of the CPU itself has now expanded to the point where floating point operations can be supported natively at their full size, you don't really need coprocessors anymore, but the technology that went into the coprocessor development eventually got integrated into the CPU itself. And that's what supports floating point operations. It's been a very long and storied development from a hardware perspective. So floating point operations are fast and efficient. They are your fast, efficient option. And very often, they're good enough. Like use of that like absolute value and checking for less than epsilon trick, that's more efficient than these libraries, right? But, you know, they still exist. It depends on what you're doing, right? Yeah. So basically, you've got three options for dealing with floating point precision error, right? You've got represent it as a floating point and just deal with the error by not using equality comparisons. You've got use the decimal library, and you've got use the fraction library, but that only works if the numbers are rational, because only rational numbers can be represented by fractions. But only rational numbers can be represented by finite series of characters as well. You know, whatever. But anyway, so if you want to use the decimal library, from decimal, import decimal, right? You can actually like abbreviate this to D and it would still work. What you're doing here is you're picking a name that you're referring to this thing in the, well, no, you need as at the end. I'm sorry, pardon me. So if you did, for example, from decimal, import decimal as D, then you can just replace every instance of this big long decimal word with the letter that you specify here, and it would just work if you don't like typing that much, which you shouldn't. You shouldn't like typing that much. You should be lazy. Anyway, so decimal, it's a bit, there's one tricky point about decimal that you need to know in order to be able to use it properly. You have to not put a floating point number into it to begin with, right? You must represent it in one of two ways. You must represent it using whole numbers plus arithmetic operations, or you must represent it as a string. If you feed a floating point number into it, it will just interpret that as with the floating point error included, because you've given it a float, right? So you have to not give it a float in order for it to behave like it's supposed to. Does that make sense? Good. Any questions? Okay, good. So, why not use decimal all the time? Because it is much slower than floating point operations. I have already talked about that, but, you know, there you go. There's a slide that says that too. So, the alternative to that is the fraction library. From fractions, import fraction. We have fraction 1 divided by fraction 3. We get fraction 1, 3. This is essentially, if you imagine a little slash right there, that's perfect, right? Conversion between float, decimal, and fraction reveals differences in representation. So, what we're doing here is we're using object-oriented programming to provide a different number format, essentially, that's different from the native representation that's inside of Python. When you view a fraction from the fractions library, it's represented as a fraction object, right? We're going to get into objects in a couple of weeks, but essentially, an object is a way of packaging up data with methods, with functions. You have data that has been combined with procedures. So the data in this object is, you know, what is the numerator, what is the denominator, those values, that's the data. What are the operations? How do you perform division? That's the operation. How do you perform addition, subtraction, multiplication, etc., etc., etc.? Does that make sense? Good. So, in closing, what do we do about floating point representations? Well, there are a few different strategies, aside from the ones that we've already covered. You can in a lot of cases, you can actually avoid using floating point altogether if you simply like move the decimal place back a couple of notches. And if you're dealing with time, right, and you don't if you never need to measure anything less than a millisecond, then just do it in integers as milliseconds, and then divide it out to find seconds if you need to, right? That way you don't lose any precision. Dollars and cents is another good example of that. 2, use the decimal or fraction standard libraries. They are slower, but they work if you know how to use them. You can use a library for interval arithmetic. The float gives safe lower and upper bounds, takes twice as much memory and time. Use problem-specific libraries or check literature for algorithms with known numerical properties. So if you're performing this type of math, check to make sure that there isn't a library that already exists, that already does the math you're trying to do, and handles all of these problems for you, so you don't have to think about them. That's kind of the whole point of software, right? Code reuse. Use symbolic computation in a computer algebra system instead of a programming language. Right, yeah, that's not really good advice for this class. When using float, never compare for equality. Check results within tolerance. When using floating point representation, never compare for equality. Ever, for any reason, or I will find you. Class dismissed.